Hello everyone. So today we are going to discuss principal component analysis using R. In many studies we have to deal with a large number of variables, and often it becomes very difficult to handle such huge number of variables and also in interpreting them. Naturally, a reduction in the dimension of the number of variables is desired. One such dimension reduction technique is known as the principal component analysis. Now, we have already learned about the theory behind the principal component analysis, and today we are going to mainly focus on the applications of the principal component analysis through examples. Firstly, we are going to look at a graphical interpretation of principal component analysis. We will further look at an example where it is worthwhile to perform the principal component analysis, and also an example where principal component analysis is not worthwhile. We will also discuss the cases where principal component analysis is actually worthwhile and where it is not worthwhile. Learning objectives. So, we are going to first give a quick review of principal component analysis and a few results on principal component analysis. Then, we are going to look at the geometric interpretation of principal component analysis. Next, we will deal with an example where principal component analysis is worthwhile, followed by an example where principal component analysis is not worthwhile, and lastly we will summarize our findings from today's lecture. So, let us have a quick review of principal component analysis. For a more detailed description, one can refer back to the previous modules about the theories on principal component analysis and the results. So, suppose X is a vector of m variables with the correlation matrix R. Let lambda 1 greater than equal to lambda 2 greater than equal to lambda m be the eigenvalues of the matrix R. Then the jth principal component of the variables x1, x2, xm is given by yj equal to pj transpose x, j running from 1 to m. Here Pj is the normalized eigenvector corresponding to the eigenvalue lambda j of the matrix R. So, let us have a quick review of a few results on principal component analysis. The variance of the jth principal component yj is given by lambda j, where lambda j is the jth eigenvalue of the correlation matrix R, and j runs from 1 to m. For the two principal components yj and yk, where j and k are not equal, we have the covariance between yj and yk is equal to 0. Then the sum of the variance of the principal components yj's, j running from 1 to m, is the same as the sum of variances of the original variables x1, x2, xm. The proportion of the total population variance explained by the kth principal component is given by lambda k by lambda 1 plus lambda 2 up to lambda m, and here k runs from 1 to m. The cumulative proportion of the total variability explained by the first j principal components is suppose denoted by capital Pj. It is given by summation k from 1 to j lambda k by lambda 1 plus lambda 2 up to lambda m, and j runs from 1 to m. If this Pj value exceeds some predefined percentage like 85% or 90%, then we work with the first j principal components instead of the original set of variables x1, x2, xm. So, first we look at a two-dimensional example where we can have a look at the graphical interpretation of principal component analysis. For that, we get an arbitrary data x of the given values and y of the given values. Let us first plot the given data. We do this in R with the help of the command plot followed by the variable x of values and the variable y of the given values. This is how the plot of the data looks like. For principal component analysis to work properly, we must have that the data be mean centered. So, we first center the data, that is, we subtract from the data x the mean of all the x values and we subtract the mean of all the y values from every component of the variable y. Next, we plot the mean centered data using the plot command in R. This is how the plot of the centered data looks like. First, we move on from the topic and we first discuss about what we mean by an orthogonal transformation. Consider a linear transformation from the variables x, y to the variable u v, where u v is given by the following transformation with the help of the matrix A, which is a matrix of order 2 cross 2. If in particular this matrix A is an orthogonal matrix, then we say that the linear transformation is an orthogonal transformation. So, a natural question that arises is, what effect does this orthogonal transformation have on the axis? Any linear transformation basically leads to a rotation of the axis. An orthogonal transformation also leads to a rotation of the axis, and orthogonal transformation retains the orthogonality of the axis. So, here is in particular one such orthogonal transformation of the axis. If we rotate the axis further, then we have another orthogonal transformation of the axis, which is given by this second plot. So, this is all about orthogonal transformation. So, we come back to our topic of principal component analysis. First, we need to find the variance covariance matrix of the mean centered data. We first combine the data in the form of a matrix, and using the R command COV followed by the data, we find the variance covariance matrix, which we store as COV.m. Next, we find the eigenvalues corresponding to the covariance matrix, and we extract the corresponding eigenvalues with the help of the R command $values from the R object COV.eig. Next, we find the cumulative percentage of the variability explained by the principal components. So, here we have the cumulative proportion of the variability explained by the principal components. Note that the first principal component explains about 96% of the total variability in the data. So, instead of working with the original two variables, we can work with the first principal component without significantly losing much information. Next, we plot the centered data along with the direction of the principal components. We do this with the help of the R command plot, and we draw the principal components with the help of the R command AB line. So, here we have the plot of the mean centered data and the two principal components. So, this is the first principal component and this is the second principal component. So, note that principal component is basically an orthogonal transformation of the axis, and the orthogonal transformation is so chosen such that the variation along the first principal component is maximum and the variation along the second principal component is minimum. So, this was about the graphical interpretation of principal component analysis. So, here we find the eigenvector corresponding to the largest eigenvalue. We can extract it from the R object cov.eig followed by dollar vectors, and the comma 1 gives the first eigenvector. So, here we have the first eigenvector. The first principal component is then given by the linear combination of the original variables, and the coefficients are given by the components of the eigenvector p1. If we have the data on the first principal component, we can optionally recover the original data by an approximation, and if we have both the principal components, we can recover the original data back by 100%. So, since principal component is an orthogonal transformation of the data, we can revert the transformation and get back to the original data set. So, we revert back to the original data set using only the first principal component. Here we have the recovered data set from the considered first principal component. If we plot this original data set, that is the recovered data set from the considered principal component, this is how the plot looks like. Notice that in this plot the variation over the second eigenvector is gone because we have not considered the second eigenvector. Next, we are going to look at a data and we are going to perform principal component analysis on this given data. The data gives the time taken by a number of athletes in completing different races like a 100-meter race, 200-meter race, etc. Note that the time taken to complete the 100-meter race, 200-meter race or the 400-meter race is given in seconds, whereas the times taken for completing the other races are given in minutes. There are several functions from different packages to perform the principal component analysis. The functions like prcomp, princomp are from the built-in rstats package. Several other functions include the function pca from the R package, factomine R, the function doD.pca from the R package ADE4. Now, the function princomp uses the spectral decomposition approach, whereas the functions prcomp and the function pca uses the singular value decomposition approach. According to our help, the singular value decomposition has a slightly better numerical accuracy, and therefore, in our study we are going to consider the R function prcomp. So, for our given data, we use the R command prcomp and we mention over here the argument scale equal to true. Now, this is needed because the times taken for completing the different races are in different units. Scale equal to true implies that the variables are first standardized and after that we perform the principal component analysis. So, from the R object runner.pca, if we extract the component SDEV, these give the square root of the eigenvalues corresponding to the correlation matrix of the data. So, the eigenvalues are in decreasing order of magnitude if we extract from the R object runner.pca the component rotation, the columns given under this rotation will actually give the eigenvectors corresponding to the eigenvalues. So, we first find the eigenvalues of the correlation matrix R. As I mentioned before, that if we extract the component SDEV from the R object runner.pca, this gives the square root of the eigenvalues. So, we basically square them to obtain the eigenvalues. We also find the percentage of the variability explained by the different principal components and also the cumulative percentage of the variability explained by the different principal components. For simplicity, we basically arrange them in a data frame and we have the following. So, we see from the third column that the first principal component explains about 83% of the total variability and the first two principal components explain about 94% of the total variability. So, next we look at the scree plot using the base graphics. So, here is the R command for the bar plot and we add line segments to the plot, and this is how the scree plot looks like. Note that the first two principal components retain about 94% of the original data variability. So, instead of the original 8 variables, we may work with the first two principal components without losing much information. Hence, we may conclude that we have a reduction in the dimension. Instead of using base graphics, we can also use our package Facto Extra for various visualizations of principal component analysis. The package can be installed and loaded as follows. Under the package Facto Extra, the R command fviz_screeplot followed by the R object of the class PRComp will give the scree plot. So, this is how the scree plot looks like as we saw before. So, next we look at another example. Here we have x to be a vector of 6 variables with the given correlation matrix R. So, from first principles, we first find the eigenvalues corresponding to the correlation matrix R using the R command eigen and then extracting the values. So, this is the eigenvalues in the decreasing order of magnitude. Next, we find the cumulative proportion of the variability explained by the different principal components. So, here is the cumulative proportion of the total variability. We see from the above table that the first 5 principal components explain about 93% of the original data variability. Thus, we may conclude that there is not much significant reduction in dimension if we consider the first 5 principal components instead of the original set of 6 variables. So, this is an example where principal component analysis is not worthwhile. So, we also see from the scree plot the R command is as given. So, this is the scree plot. We see that here we have a elbow. So, the first elbow is seen corresponding to the index 2, but the first two principal components do not explain much of the original data variability. So, there is not much significant reduction in dimension, and this occurs due to the fact that the variables might have very low correlation among themselves. So, to conclude, we see that we can use several inbuilt R functions to perform principal component analysis, or we can perform principal component analysis from the first principles. If the variables are highly correlated amongst themselves, then we can achieve significant reduction in dimension by using the principal component analysis. However, if the variables are not much correlated amongst themselves, then it is not worthwhile to perform the principal component analysis, in the sense that we do not achieve significant reduction in dimension.